Welcome to your deep dive. Today, we're going into the world of distributed consensus algorithms.
hmm
These algorithms are kind of like the hidden heroes behind the scenes of large-scale software systems,
Hmm?
making sure that all the different computers can work together, even if some of them fail.
It's like, when you have a network of servers powering something like Google or Amazon.
Yeah.
They all have to agree on every single decision they make, even if some servers crash or the network has problems.
Right.
That's really where these algorithms shine.
So we're talking about keeping all those computers on the same page no matter what's happening. And today we're diving specifically into Paxos and Raft,
Right.
two big names in the field.
Yeah.
Now, Paxos has been around for a long time, but it's known for being really complex.
Yeah, you can think of Paxos like you're trying to decipher ancient hieroglyphics. It gets the job done,
Uh-huh.
but it takes a lot of expertise to understand.
Okay.
Raft, on the other hand, is more like reading a really well-written instruction manual.
Oh.
Both of them can achieve consensus, but one is way more approachable.
So for our deep dive today, we're using Raft.pdf and
Mhm.
Paxos Made Simple.pdf. And our mission is to try and help you all grasp the core concepts of these algorithms.
Yeah.
And don't worry, we're going to cut and rest decipher those hieroglyphics together.
Yeah. So the main problem that these algorithms are trying to address is how to create something called a replicated state machine. Imagine you have to make a bunch of servers act like they were a single, really reliable machine. Each server has a copy of the same data, and it has to run the same commands in the same order, almost like you're doing a synchronized dance routine.
I like that analogy. But if it's already so complex, how did Paxos become the most popular algorithm for such a long time?
Well, Paxos has been around for a while, and it works.
Right.
But its complexity comes from how it approaches consensus. It focuses on getting agreement on just one decision at a time, almost like they're planning out every single step of a dance. And because it treats all servers as equals in a peer-to-peer approach, it becomes kind of difficult to keep track of everything that's going on.
That sounds pretty hard. So then Raft comes along and promises to be much more intuitive. How does Raft change things?
Well, instead of everybody trying to lead at the same time, Raft uses a strong leader, like the conductor of an orchestra. That leader orchestrates the whole process, which makes the flow of information and decisions much simpler.
So one clear decision maker. That makes sense.
Exactly. And another key innovation in Raft is the focus on log replication. Think of it like a to-do list of all the commands that have to be run.
Okay.
The leader adds new commands to its log, and then every other server copies those commands onto their own logs. This makes sure that everybody stays in sync.
So it's like having a synchronized to-do list across the entire system.
Exactly.
I'm starting to see why people think Raft is easier. It uses these very clear roles and mechanisms to simplify a really complex problem. But what about safety? How does Raft make sure that, things don't go wrong, especially when things start to fail?
Safety is really important in these systems. Raft deals with it through a few different mechanisms. For example, if the leader crashes, Raft uses randomized timers to quickly and efficiently elect a new one. It's kind of like every server is drawing a random straw, and whoever's timer runs out first gets to be the new leader.
Oh, okay.
It's a very democratic way to pick a new leader.
Yeah, I like that. It seems like a really smart way to avoid arguments and make sure that there's a smooth transition of power if something goes wrong.
Right.
The Raft paper also mentions some other interesting details, like using something called terms as a logical clock. What is that?
It's a clever way to keep track of time in a distributed system. Each term is like a new chapter in the history of the system.
Oh, okay.
And servers can look at that chapter number to see if they're up to date, making sure that everybody's on the same page. It's a very efficient way to spot and handle outdated information.
So if a server is stuck back in an earlier chapter, it knows that it needs to catch up, right? Okay, this definitely highlights how much Raft cares about being easy to understand. Now, let's see how the Paxos Made Simple.pdf paper handles the same problem, but with a very different approach.
Right. This paper breaks down Paxos into three main roles:
Mm.
proposers, acceptors, and learners.
Okay.
Proposers are like choreographers who come up with new dance moves.
Mm-hmm.
Acceptors are like dance captains who decide which moves to include.
Right.
And learners are the dancers who actually perform the finished dance.
That sounds like a very intricate system. How does it guarantee that only one value or dance move is chosen?
Paxos makes safety its #1 priority. It ensures that only one valid dance move or value is selected, and it also makes sure that all the learners are guaranteed to perform the same move.
So no rogue dancers doing their own thing.
Precisely. But, earlier you mentioned that Paxos can have trouble making progress.
Yeah.
The paper acknowledges that if there isn't one designated proposer to drive the process, you can have situations where no proposal is ever chosen. It's like having a bunch of choreographers arguing about what the next move should be. The dance would never even start.
Right. I can see how having that one leader in Raft is a lot more efficient and keeps things moving smoothly.
Exactly.
If we take a step back and look at both of these papers, what are the biggest differences that stand out to you?
Well, the most obvious difference is their approach to achieving consensus. Raft really emphasizes simplicity and understandability, almost like a well-structured symphony.
Okay.
Paxos, even though it's been simplified in this paper, still retains a certain level of complexity. It's kind of like trying to understand a free-form jazz improvisation.
That's a good way to put it. So both of them are beautiful and serve a purpose, but they require different levels of expertise to really appreciate, right? I think you were saying earlier that both papers emphasize safety, but they come at it from different angles.
You got it. Paxos is all about being very meticulous in choosing the right dance move, if you will, making sure that only the correct values are chosen. Raft, however, really focuses on synchronizing the entire performance, ensuring that every server is executing the same commands in perfect harmony.
So Paxos is the super careful choreographer, and Raft is the conductor who makes sure that everyone is playing from the same sheet music.
Precisely.
All right, so we've gone pretty deep into the core ideas of both Paxos and Raft. Now let's shift gears a little. What about real-world uses for these algorithms? It seems like they could be used for way more than just managing data in really big systems.
Oh, absolutely. The applications go way beyond that.
Okay.
For instance, consider blockchain technology.
Yeah.
At its core, blockchain relies on distributed consensus to create a secure and tamper-proof record of every transaction.
That's really interesting. So instead of a central authority, like a bank, verifying all the transactions, you have a bunch of computers agreeing on the validity of each one, using algorithms like Paxos or Raft.
Exactly. Each new block added to the chain represents a set of transactions that everybody has agreed on. And that agreement, that consensus, is reached through these distributed consensus algorithms.
So it's like replacing that central trust with this distributed mechanism. That's really clever. What other examples can you think of?
Well, let's take online gaming. Games with tons of players, massively multiplayer online games, those need real-time coordination between players all over the world.
Right.
Distributed consensus could be used there to make sure that everyone experiences the same game events in the same order, regardless of network lag or server issues.
That would definitely cut down on a lot of frustration and arguments between players. It's really cool how these algorithms bring order to what could be a total mess. Let's go back to the Raft paper for a minute. They talk more about how Raft deals with situations where the server logs don't match. Can you remind me what a server log is again?
Of course. Remember how we talked about Raft's focus on keeping a consistent log across all the servers? It's basically a record of every command that's been carried out. You can think of it like a really detailed timeline of everything that's happened in the system and make sure that every server has the same history.
Right, right. But things can get complicated when leaders crash. That could leave some of the servers with logs that are missing information or even conflict with each other.
Yes.
So a follower's log might end up looking different from the leader's log. How does Raft fix those inconsistencies?
Raft takes a very direct approach. The leader makes the follower's logs match its own. It basically overwrites any conflicting entries to make sure that everything is consistent.
So the leader's log becomes the ultimate truth, making sure that all the servers end up with the same information. That makes sense, but doesn't that kind of contradict Raft's principle of strong leadership? I thought the followers were supposed to, well, follow, not be overridden.
That's a good observation. But this overwriting, together with a very specific rule for elections, ensures that the system stays safe. Remember how we were talking about how a candidate for leadership needs to have a log that's at least as up-to-date as most of the servers?
Yeah, it's like a new conductor coming in. They have to have the whole score. They can't be missing parts or be working off an old version.
Right, and that rule guarantees that a new leader will always have all the finalized entries from previous terms.
Okay.
Another important thing is that entries in the log only move in one direction, from the leader to the followers. Leaders never change their own entries, and they make sure that the followers' logs match up with theirs.
So it's a one-way street for information. And the leader's like the traffic cop. This simplifies things a lot, doesn't it?
It does. This one-way flow makes it much easier to finalize entries from earlier terms. Raft never finalizes older entries just by counting how many copies there are. It only does that for entries from the current leader's term. And once an entry from the current term is finalized, all the previous entries are automatically finalized as well because of that log matching feature.
That's a great way to explain it. It prevents conflicts where an older entry might seem final, but could still be changed. So Raft have all these checks and balances to make sure that information goes in the right direction and everyone's on the same page. But how can we be absolutely sure that this approach guarantees safety? Is there any proof of that in the paper?
Oh yes. The paper actually uses a very clever technique called proof by contradiction.
Okay.
They start by assuming that something called the leader completeness property is not true, meaning a leader might miss some finalized entries. Then, they show how that assumption leads to a contradiction, proving that the leader completeness property must always be true. It's a common technique in mathematics to prove a concept.
So basically, they're saying if this wasn't true, then everything else we know would fall apart.
You got it. They walk through the steps of the algorithm and all the rules, demonstrating how that impossible situation just can't happen.
I'm really starting to appreciate how carefully Raft is designed, with every little detail carefully thought out to guarantee these essential safety properties.
And don't forget, this leader completeness property directly leads to what's called the state machine safety property, which makes sure that if a server has applied a log entry to its state machine, no other server can apply a different entry for that same spot in the log.
So all the state machines across the whole system will always be synchronized, running the same commands in the same order. That's what we ultimately want, right?
Exactly. And the paper doesn't stop there. It also talks about what happens when a follower or candidate server crashes.
I bet that's much easier to deal with than a leader crash, right?
Much easier. If a follower or candidate crashes, any future request sent to it will fail. But Raft handles it gracefully by just retrying over and over again. If the server comes back online, the request will eventually go through. It's a very resilient system.
Like knocking on a door until someone finally answers.
Perfect analogy. And since the requests are designed to be what we call idempotent, it means that even if a server gets the same request a bunch of times, it won't cause problems. It's like pressing the elevator button over and over. It's not going to make the elevator come any faster, and it won't break anything.
That's a good point. All of this sounds great in theory, but does the paper talk about how Raft actually performs in practice?
They did some performance tests, see how quickly Raft can elect new leaders and how much downtime there is after a crash.
Oh, okay. So they didn't just rely on the theory, they actually put Raft through its paces.
Right.
And what were the results?
Very promising. They found that even a small amount of randomness in those election timeouts is enough to avoid split votes where no leader gets elected.
So those random timers, like drawing straws, really work.
But they do. They discovered that with just a little bit of randomness, the system could elect a new leader and get back up and running in just a few milliseconds.
That's incredibly fast. It really seems like Raft lives up to its promise of speed and reliability. What about those timing requirements we talked about earlier? Did they confirm those as well?
Absolutely. They found that if you make the election timeouts too short, it can stop leaders from sending out those heartbeat messages, which can lead to unnecessary leader changes. They recommend using a slightly longer timeout to get a good balance between being quick and keeping the system stable.
It's all about finding the right balance. What about other algorithms? How does Raft stack up against the competition?
The paper does say that a lot of people have tried to solve this distributed consensus problem. They mention tweaks and improvements to Paxos and some completely different approaches, like view-stamped replication.
So Raft's not the only solution, but it seems to have some unique advantages, like being easy to understand and implement.
Exactly. They highlight how Raft's use of a strong leader, where picking the leader is a core part of the design, not just an optional extra like in Paxos, makes it much simpler, both to understand and to actually build.
It's like having a clear chain of command that can be super valuable in a system this complex.
Right. The paper also points out that Raft's messages are much simpler compared to other algorithms. It achieves all its goals with fewer and clearer messages,
Yeah.
which can make it run faster and be easier to debug. It's kind of like trying to communicate using a complex code versus just using plain language. Simplicity is often better.
Absolutely. It's about being elegant and efficient. Are there any downsides to Raft's reliance on a strong leader? Does the paper talk about any limitations?
They do admit that while the strong leader makes many things simpler, it might not allow for certain performance optimizations that you can get with other approaches. One example they give is something called egalitarian Paxos, or Paxos, which can take advantage of the fact that some commands can be executed in any order. That means it can sometimes perform better in certain situations.
So ePaxos might be faster sometimes, but it's probably a lot harder to understand and implement.
Yeah, it's always a trade-off. If simplicity is your main goal, Raft seems like the best choice. But if you need to squeeze out every bit of performance and are okay with more complexity, ePaxos could be a better fit.
It's like picking between a user-friendly car and a high-performance race car. Another area where Raft stands out is in how it handles changes to the cluster membership, like adding or removing servers, which we talked about earlier. Can you remind us about that?
Right. Raft uses a smart two-phase approach that uses a special transitional configuration.
Oh, yeah.
It allows servers to move between different configurations at different times without risking the safety of the system.
So you don't need to stop the entire system to add or remove servers. Raft keeps things running smoothly even when things are changing.
Exactly. This mechanism doesn't add much overhead to the main consensus protocol. It's a really neat and efficient solution. The paper compares Raft's approach to what other systems use and shows how Raft does it with much less complexity and with fewer rules.
It's like a really well-choreographed dance. The dancers can join or leave the stage without missing a beat.
And speaking of performance, the paper wraps up by really emphasizing the importance of how easy an algorithm is to understand.
Okay.
They argue that even if an algorithm is theoretically perfect, it's useless if developers can't grasp it well enough to implement it correctly in the real world.
You're absolutely right. An algorithm is only as good as its implementation in real-world system.
Right. Raft was designed with this in mind from the beginning. It focuses on clarity and simplicity to make it easier for developers to understand, implement, and build on.
And judging by their user study and how popular Raft is becoming, it seems like they've accomplished that goal. It's really cool to see Raft gaining popularity and maybe changing how we think about distributed consensus. It seems like a really strong alternative to Paxos, which can be so complex. But before we wrap up, I have one more question about the paper. We've talked about how Raft keeps this log of every command, but wouldn't that log just keep growing forever? It seems like that could cause problems for storage space and performance over time.
You've hit on a really important point. You're right. If we let it grow unchecked, the log could become this massive digital monster,
Right.
taking up tons of storage and really slowing down the system. But luckily, Raft has a very smart way to handle that. It's called log compaction.
Log compaction. It sounds like cleaning up your computer. How does Raft clean up all those log entries?
It does it through a process called snapshotting. Imagine taking a panoramic picture of the system's entire state.
Okay.
This snapshot captures everything important without needing to keep track of every single log entry that led up to that point.
So instead of having every single detail in a huge library, you just have a snapshot of the most important information.
Exactly. In Raft, each server can independently create snapshots of its own finalized log entries.
Okay.
And these snapshots not only store the current state of the system, but also some key metadata, things like the index and the term of the last log entry that it replaces.
So it's like putting a bookmark in and saying, this is where we are now, and everything before this is captured in the snapshot.
That's a great way to put it. And that metadata makes sure that any new entries that are added after the snapshot still work correctly with the snapshot state. It helps keep those consistency checks we talked about earlier working properly.
It makes sure the story flows smoothly, even if you condense a big part of the log.
Okay, this is starting to make sense, but I have another question. If each server creates snapshots on its own, doesn't that go against Raft's idea of having a strong leader? I thought the leader was in charge of everything. That's a very sharp observation. It's a valid concern. But the designers of Raft argue that making this exception for snapshotting makes sense.
Interesting. Why do they think that?
They point out that for the entries that are being snapshotted, consensus has already been reached.
Okay.
Remember, the log is all about decisions that have already been made and finalized, so there's no chance of creating conflicts or inconsistencies when servers create their own snapshots.
Right, because those decisions have already been made. It's like the leader has finished choreographing the dance up to a certain point, and now each dancer can take a picture of that final pose without stepping on anyone's toes.
Exactly. This approach has some practical benefits, too. It saves on network traffic, because each server can create its own snapshot locally, without having to download a large file from the leader.
So it's much more efficient for everyone to just take care of their own snapshots instead of relying on the leader for everything. But what if a follower is way behind and its log doesn't even have the entries that are covered by the leader's latest snapshot? How does Raft handle that situation?
That's something the paper addresses.
Yeah.
In those cases, the leader steps in and sends its snapshot directly to the follower that's behind.
Mm-hmm.
It uses a special request called install snapshot.
So the leader is like a helpful coach, giving the follower the missing pieces they need to catch up.
Precisely. The follower can then replace its old log with the leader's snapshot, and boom, it's back in sync with everybody else.
Okay.
Now, snapshotting is a really useful tool, but there are still some performance things to consider. It's not a perfect solution that solves all log compaction problems.
Well, what kind of challenges can still come up, even with snapshotting?
One challenge is deciding how often to create snapshots.
Okay.
If you create them too often, you're wasting resources.
Right.
But if you don't create them often enough, you might run out of storage space.
Uh-huh.
Or it could take much longer to recover if you have to restart a server.
So, like, finding the right balance between keeping things tidy and not spending all your time cleaning?
Yes, exactly. The paper recommends a simple strategy. Create a snapshot when the log reaches a certain size. This helps to keep the overhead low, but also ensures that snapshotting happens often enough to avoid running out of storage.
That sounds reasonable. But what about the actual process of creating the snapshot? Doesn't that take time?
Right.
And could it slow down the system while it's happening?
You're right. Writing a snapshot for a large system can take some time.
Yeah.
To
Yeah.
deal with this, the paper recommends using techniques like copy on write. This lets the system keep processing new updates, even while a snapshot is being created.
So the system can keep running smoothly in the background even while it's taking a picture of its current state.
Precisely. It seems like Raft has really thought of everything to make this as efficient and safe as possible.
Yeah, it really does. They've really considered every angle.
Yes, that attention to detail and focus on real-world use are big reasons why Raft is becoming so popular.
Mm-hmm.
It's not just a theory, it's a well-designed system built for real-world applications. And they even tested it in a real production environment.
Oh, really? That's awesome. Tell me more about that. It's really interesting to see how Raft works beyond just those performance experiments.
They mentioned that they implemented Raft in a system called RamCloud.
Okay.
It uses Raft to manage configuration information and to handle what happens when a coordinator fails.
That's pretty cool. So Raft is being used in a live system to solve real problems.
It is. And they also mentioned that there are some open source implementations of Raft available,
Oh, cool.
which means there's a growing community of developers who are using and supporting this algorithm.
It's exciting to see Raft's potential and how it's changing how we think about distributed consensus. Before we wrap up, let's take a minute to think about everything we've covered today.
Sure.
We started by exploring this fundamental challenge,
Mm.
how to achieve agreement in a distributed system. And then we dug into the complexity of Paxos and the elegant simplicity of Raft. We've seen how these algorithms are the unsung heroes, bringing order and reliability to those complex systems that power so much of our digital lives.
We learned how Raft, with its focus on a strong leader, log replication, and those built-in safety mechanisms, offers a much more approachable way to achieve consensus compared to the complexity of Paxos. It's like choosing a clear set of instructions over trying to solve a really difficult puzzle.
Definitely.
And we saw how Raft goes beyond just the theory. It addresses practical problems like log compaction, changing cluster membership, and gracefully handling all kinds of failures.
It's been a fascinating journey, and I hope everyone listening has gained a better understanding of these hidden systems that make our distributed systems work so smoothly.
And remember, this is just the beginning.
Great.
There's so much more to discover in the world of distributed consensus. We really encourage you to explore further, read those papers we discussed, and keep learning about this exciting field.
We'll make sure to include links to those resources in the show notes. And who knows, maybe this deep dive will inspire you to come up with your own innovative distributed systems using Raft or other cutting-edge algorithms. The possibilities are truly endless.
They are. Keep exploring, keep learning, and we'll see you next time.